Welcome back. Today we are solving one of the organic chemistry problems from the International Mendeleev Chemistry Olympiad 2016. I will walk you through the complete solve process from start to finish, as always. Quick announcement before we start. I know many of you are actively preparing for IChO 2026 right now. Starting from June 6th, I am hosting live sessions where I solve the organic and inorganic problems from the IChO 2026 preparatory problem set together. I will cover 13 problems across 4 sessions. Each session is 90 minutes with an additional 30 minutes of Q&A at the end where you can ask me anything directly. If you want to join, everything you need to know about this short program is in the description below. Now let's get into today's problem. This is honestly a very challenging question with lots of interesting transformations and some new reactions that we will learn along the way. Again, we start skimming through the whole problem. When I say skimming, I mean this 2 to 3 minutes investment in the beginning that you have to do to see how the problem is structured, and most importantly, if there is any dependency between parts. So as you can see, they give information about Robinson annihilation, they show some mechanism and some example from the starting materials to the product. Then they give information about ciphered compounds X and Y that belongs to the first subproblem. Then there is second subproblem and the third one with some preceding information. That's basically the whole problem. And as for the dependency between the subproblems, subproblem 1 and 2 are dependent on each other on the structure of X, as you can see here. So that means we should find the structure of X from the first subproblem, which serves as the starting point in the second subproblem. That's the only dependency between the parts. So this is what I was talking about. Usually the problems we have solved up until now, they are separate entities. They didn't have relationship with each other. But here, specifically, the structure of X is absolutely necessary for us to start solving subproblem 2. But other than that, there is no any relationship. Like subproblem 3 on its own, this scheme has nothing to do with the information given us in previous parts, except the fact that we have to know the Robinson annihilation, the mechanism, and everything. So let's start with the subproblem 1. Here they talk about Robinson annihilation. That's a very important reaction in the synthesis. And then it's ketone deprotonation, Michael addition, and then aldol condensation. So ideally, we have to know this. This is what we learn in our organic chemistry. That's in alpha carbon chemistry chapter, where we learn specific reactivity of alpha carbon, where if there's hydrogen, it's acidic, it can be deprotonated, and can serve as nucleophile in wide variety of reactions. So that's one of them, specifically Michael addition. And Robinson annihilation is just Michael addition followed by aldol condensation. These two reactions together is called Robinson annihilation. So we already know the mechanism. We deprotonate the acidic proton, then we do Michael addition, 1,4 addition, and then we do aldol condensation. That's accompanied by the loss of water, and we get this alpha-beta conjugated ketone. And now here they talk about X and Y, so we have two short reactions. For X, it says product of Robinson annihilation, so we expect something similar to this. For Y, there is no two annulated rings, so we have two annulated rings here. So we expect similar in X, but not in Y. And also in Y, there are two different CO groups. So based on this information, we need to find X and Y. As you can see, for Y, we have two important pieces of information that we need to keep in mind, right? That it does not have two annulated rings, as in usual case, and it has two different CO groups. So we have to keep that in mind, but let's start with solving for X first. So X is quite easy. You need to find out the most acidic proton. So just to remind you, there's also another possibility here that this base can deprotonate this hydrogen in this alpha position because it has two different alpha positions, but we do little pKa comparison because this hydrogen here has pKa around 9 because it's between two CO groups, but this hydrogen in this alpha position has pKa around 18 to 20, right? That's a typical pKa of alpha hydrogens. So obviously the conjugate acid of this base, it has a pKa around 16. So obviously it's gonna deprotonate this one and it will be essentially irreversible. The equilibrium will mostly derive to the right. So that's why I'm just talking about these two possibilities, but I just want you to not directly jump onto this, but think that this is actually the most acidic proton, but there is somewhere another possibility, maybe not in this problem, but another problem you might think of this possibility, even though it's less likely to occur. So after we deprotonate that hydrogen, we get a negative charge here, and we do this 1,4 addition, and then we get our Michael addition product, and then using the hydrogen that base took in the first step, we are protonating to the ketone, and then we do our aldol reaction first. So this is aldol addition product, and then through E1CB mechanism, this water is eliminated, so we get our final structure of X. And obviously we eliminate this water to the left with this hydrogen so that we can get conjugated system here, because there's one more possibility here as well, so that we can install a double bond on this side, but that doesn't add any structural stability. I also specifically mentioned about the bases here, just to prove that the base that we use here is just in every step it takes the proton and it leaves as BH plus in the protonated form, and then that proton in the protonated form is used in the subsequent steps. So we use the base, but we regenerate the base. We use the base, or we regenerate the base. We regenerate the base and the water leaves. So that shows that the base here, which is etoxide, is the catalyst that's regenerated at the end of the reaction. And obviously this matches with the molecular formula given here: 11 carbon atoms, 2 oxygens, and 1, 2, 3, 4, 5 hydrogen deficiency index. We don't need to count all hydrogens. Though in this case, it would be really easy, because 1, 2, 3, 4, 5 multiplied by 2, which is 10, 3 here, 13, and the 1 here, 14. So it makes perfect alignment with this molecular formula. So that's a structure of X that we will be using in the subproblem 2 as well. So we have to make sure that we get this correct. For the second part of the subproblem 1, we know that there are 2 pieces of information. So we have to keep that in mind. So we first start with a Michael addition product, right? That's quite easy. We have our negative charge here, and then it attacks here, and then this goes here, and then there is this protonation that happens to yield this product. And obviously there is only one possibility, because this alpha positions here, there is no any hydrogen. So that's why there's only one possibility. Starting with this nuclear valve, we get our Michael addition product. Now, I would like to show all possibilities that we can have with this Michael addition product. So that's why we are labeling our carbon atoms that are necessary for me to show all of these possibilities. And as you can see here, these carbons, some of these carbons, let's say carbon labeled as A, hydrogen attached to carbon A can be deprotonated and can give a negative charge, and it can attack, for example, carbon labeled as G, and then it will go, and then we can have this new ring. So that's why I labeled, to show the all possibilities in this form, where, for example, in the first case, carbon labeled A becomes negatively charged and attacks E. Okay, so this, for example, the first one shows this possibility. And in this case, it will be Claisen condensation, not aldol condensation, because we will be attacking to ester, then it will go up, comes back, and O-methyl leaves. So that's a Claisen condensation. So these are all possibilities for this specific compound. For example, let's see F and B. F attacks to B. What is this? F, here we make a negative charge, and then it attacks to carbon labeled B. Okay, so we form 4-membered rings containing F, D, C, B carbons. So these all possibilities, you can go through them, but you can see these possibilities from A to G all the way to F to E. They form annulated rings, which actually are in a disagreement with the given information. For example, let's say D to G, right? D to G, when the D attacks to G, you form this, okay? These 2 carbons are shared between 2 rings. Honestly, there's a bit of confusion about the annulation here, because annulation had no official IUPAC definition until 1994. Okay, I've been using different definitions for annulation. But in 1994, it says annulation is a transformation involving fusion of a new ring to a molecule via 2 new bonds. Okay, can use that official definition to eliminate some of these as annulation, because they involve fusion of a new ring to a molecule via 2 new bonds. Okay, about these last 2 possibilities, because when we have, let's say, C to E, where we make a negative charge and attacks to E, we do not have any annulated ring, because they have actually a bond between them, and we have rings that are connected to each other with a DF bond. But problem is that this is 3-membered ring, so that's highly unstable. Okay, that means attack of A to E is the most plausible, and we get a structure like this. So you could have arrived at the same answer by looking at the molecular formula, because as you can see, I did not use any molecular formula information. I'm just showing all possibilities here, just in case where molecular formulas are not given in some other problems. Okay, you need to be able to do this kind of analysis to go through all possibilities, to eliminate according to the given information, and so on. Okay, obviously molecular formula is given, so you should be able to use them. That's what I'm going to show you now. But sometimes you just say, oh, what if there is no molecular formula? How can I navigate through this problem? So as you can see from the molecular formula, there are 13 carbons and 3 oxygens. How about this Michael addition product, this substrate we have? It has 14 carbons, 4 oxygens. So this guy has 14 carbons, 4 oxygens, right? And then we are going to 13 carbons, 3 oxygens. So what does that mean? -1 carbon and -1 oxygen. So together it's like methanol loss. It looks like a methanol loss. Okay, that there is like only two possibilities here. We can lose actually three possibilities. Can you see them? It's one of them: A attacks to E, C attacks to E, or F attacks to E. And because C to E is highly unstable, and F to E, it's also highly unstable. Actually, we can also add it to here as well, because F to E also forms three-membered ring, but also there is annulation. Okay, we have fusion of new ring here, two molecules through two bond. So we eliminate these two possibilities, so we end up with A to E attack. But the problem is it says two different CO groups, but we have three CO group, right? So the question here becomes, how can we keep the same molecular formula as here, which means we have to write some kind of isomer for this guy, and mostly the backbone will be the same, but we need to induce a simple change here that can satisfy this requirement of having two different CO groups instead of three. So as you can remember, we have this, we said that A is going to attack E, right? So when we deprotonate here, we get negatively charged, and we just say that, oh, this directly attacks here. But as you can remember, this has resonance, right? So when we have this kind of charge here, this is enolate, which has a resonance like this. So there's also a resonance form where this negative charge on oxygen. And we have learned that oxygen can also attack. Okay, yes, there's an O attack. And we don't usually talk about this O attack in introductory organic chemistry, but you have to have this possibility in mind that you can also attack in certain cases. Usually it attacks, let's say, silicon electrophiles. When there's any silicon electrophiles, it's almost certainly O attack. Is connected to silicon rather than carbon. In general, you have to keep in mind that this is possibility. So we are eliminating this because it does not have two different CO groups. It has three different CO groups, but we are proposing a structure where oxygen has attacked, so that we are only left with two different CO groups and there is no two annulated rings. Okay, and make sure that we write square brackets for resonance structures, because this double-headed arrow and square brackets are must-have when we want to show resonance structures. Okay, we are done with subproblem 1. Okay, now we will move on to the second subproblem here. And obviously we are having this structure of X that we take from subproblem 1, because that's going to be the starting point for this subproblem. What we are going to do is we are going to focus on the synthesis, because as you can see in there's just one sentences preceding the scheme, and there is nothing useful for us to be used in the synthesis. And also this part, usually if they want to add some piece of information, they usually add at the end of here, for example, saying that write down structure formula of A to E, considering that, for example, some information about any of these ciphered compounds. But here we don't have anything, so we are going to focus on the synthesis first. So as usual, let's start with labeling the reagents with their typical roles. So first one is this hydrazine in the presence of base, typically potassium hydroxide and high temperature. That usually means Wolff-Kishner reduction. Most certainly, it's Wolff-Kishner reduction. And here, as you can see, there's tetbutoxide, potassium tetbutoxide, which almost exclusively functions as base. So it generates a negatively charged nucleophile, right? And then we have methyl iodide, which functions as electrophile. So there's a methylation expected here. And here you can see, you can use this piece of information here that there is 13 carbon atoms, but in the X from the structure given here, there are 11 carbon atoms and 2 oxygens. And B has 13 carbon atoms and 1 oxygen. So when you go from X to B, 1 oxygen is lost. Okay, so there are 2 oxygens, but here there's 1 oxygen is lost. So this confirms Wolff-Kishner reduction. We are getting rid of oxygen, right? And plus 2 carbons, because there's like 11 carbons here, and here 13 carbons. So which means we should add 2 carbons. So which means this step actually brings 2 carbons, which means there is double methylation. You can also see some, let's say, do a sneak peek to the final product, and you can see that there is like 2 methyl group here. That's probably comes from this step, okay, methylation. So we will call it like double methylation, okay? And here, next step is probably oxidation. As you can see here, there's like chromium. And what is the oxidation state of chromium in this compound? It's +6. That's the highest possible oxidation state for chromium. We know this from inorganic chemistry. Chromium can be +2, +3, +4 as well. It's not very usual, but it could be +4. Also +6, that's the maximum. So, and we usually have seen chromium-based oxidation. So because it's chromium also is in it +6, so it will go down. And you know, we can actually learn oxidant and reductant like this. If the oxidation state goes down, it's oxidizing agent. Okay, so chromium is +6, so it will go down. Maybe +4, +3. Most commonly, it will be +3. So it will act as oxidizing agent. So we know that most certainly this is going to be oxidation. And then there is this step, the CH2N2. Okay, so this has actually many roles in organic synthesis. One suggestion could be like the most obvious one, most commonly used one is converting COOH, a carboxylic acid, to COO methyl. Okay, so when we have COOH and there is this CH2N2, I'm gonna write it in full structure like this. Okay, the positive charge on nitrogen, negative charge on this carbon. So it first takes this hydrogen from carboxylic acid. That's a typical acid-base reaction, and you end up with a carboxylate and CH3N2. Okay, and then this oxygen takes CH3 and nitrogen gas leaves, so you end up having ester. Okay, methyl ester. That's one of the widely seen use cases for CH2N2 reagent. Okay, it converts carboxylic acid to methyl ester in this fashion with the evolution of nitrogen gas. Or there's also homologation or cyclopropanation, like it is also used in Arndt's ester synthesis. So we will talk about that. But one idea I would like to propose here is that it could be like this kind of reaction, because previously we have oxidation, right? So maybe we can make COOH, and then we can convert that COOH into COO methyl using this reagent. But there's only one oxygen in the molecular formula of D. That's not the case. We cannot have carboxylic acid because carboxylic acid should have at least 2 oxygens, right? So, but that's the most typical role of CH2N2. There's Arndt's ester synthesis, which means there's homologation. You add CH2 group, you enlarge the chain. But for that, we need acyl chloride. We don't have any chlorine in D. And also, it could be cyclopropanation. So I'm just putting here this all possible things that could happen: methylation, homologation, or cyclopropanation. And the last step is almost certainly Grignard, right? We have methyl magnesium bromide followed by workup, acidic workup. So, and you can also see this methyl group here and OH group here. So you can even go work backwards. You can even find structure of E. Okay, so we start with X. Okay, we apply this because here we know what's going to happen, at least for the first 3 steps. So let's start with X, and here we go to A easily because it's Wolff-Kishner reduction. So, and there are like 2 CO groups, but this CO is more reactive in compared to this carbon-oxygen double bond because it's conjugated to a double bond, so it's relatively more stable. It will not want to react. And always remember, reactivity and stability are inversely proportional. If something is more stable, like in this case in conjugated pi system, that means it's less likely to react. And so we are gonna react this CO carbonyl group with hydrazine. We are gonna form hydrazone, and then it will become CH2 group. So we will get rid of CO. And then I have got some options for B, so I will number them as B1, B2, etc. So B1 is the most obvious one, right? So you have 1 CO, and here there are 2 alpha, but this one is vinylic. So we are not gonna, we have almost never seen in, at least in basic introductory chemistry, that vinylic hydrogen, like sp2 hydrogen connected to sp2 carbon atom is deprotonated and make a negative charge. It's gonna be really unstable there. So we are making a negative charge here, and we are doing this double methylation. So that's our first option for this. So this is the most obvious one, right? So then there is B2 here. I would like to, because as you can see, not only alpha, but if you have conjugated system, your gamma position is also active here in this case, because as you can see, not only gamma position, but let's say this is alpha, this is beta, this is gamma, and every, let's say, odd position, let's say 1, 3, 5. If you have extended conjugated system, the last one in the odd position from the carbonyl group, hydrogen connected to that position is going to be acidic. So in this case, we can have a negative charge here as well, because it can be delocalized onto oxygen, right? So there's also negative charge. So we can, that proton in that position is also acidic. It can be deprotonated to have a negative charge, and then can attack to methyl iodine twice to have this structure as well. Okay, so having these candidates, we can actually find C1 and C2 accordingly, because it's just B to C is Wolff-Kishner reduction. So we are getting rid of this oxygen, and we end up with the C1 and C2. Okay, and then there is this oxidation. So the question is how and to what extent. So as you can see, molecular formula for B and D are same. So which means they are isomers, right? They have the same molecular formula, but different structures. So what that means is that they are isomers. So we just need to put CO group back, but in a position that would give a different structure. Okay? So based on proposed candidate structures, we can say that overall B to C to D is just a carbonyl shift, or maybe carbonyl and double bond shift. We are not sure about that, but they are isomers. So we are isomerizing in 2 steps. Okay, we are getting rid of oxygen, carbonyl group, and then we are oxidizing again. And here, this is just the hydrocarbon, I mean alkene, right? So when we talk about oxidation here, obviously the most reactive one would be allylic position. Okay, we are going to install oxygen here. Okay, I will talk more about this specific oxidation conditions later on. I will show you the mechanism of a similar reaction, and probably this also goes via the similar mechanism. But I will talk about that in detail at the end. But we are installing CO again, just to give the similar structure with the same molecular formula as B, right? So there are two allylic positions here and here. But if we install the CO group here, you will just get B1 again. There is no point, right? So we try the other one. So we end up with a structure like this, and we label it D1. Okay. So D1 and B1 are indeed isomers. As you can see, they differ from each other with the position of CO. And for C2, we can have a CO group here, right? But there's only one possibility. There's only one alpha allylic position that can be oxygenated, because here there is no hydrogen. Here there's no hydrogen, because in order to be oxidized, you need to have oxidizable carbon-hydrogen bonds that you can get rid of them and install oxygen, right? So there's only one alpha position that can be oxygenated, and you get D2, okay? But this B2 and D2 are actually the same thing, right? D2 is exactly the same as D2, so there is really no point in doing this. So we eliminate this pathway. And as for D1, what we can do is to speculate about possibility of this. Like, it's not an ideal choice. Why? The main question here is that what prevents us when we go from C to D, right, to this oxidation here, what prevents us installing carbonyl group to its original place, right? Because this position and this position have equal likelihood, and there's no any selectivity. I don't want to say any, maybe there might be some selectivity. This part, there's like 2 methyl group. It might be a bit sterically hindered, so maybe we can get some of more of this in compared to this. Maybe we can have, I don't know, 60 to 40% distribution between B1 and D1 if we oxidize C1. But we usually don't prefer to have this kind of situation in organic synthesis, because at the best, it gives mixture of products. Original B1, because as I said, this one allylic position or this one allylic position, they both can be oxygenated. One of them gives D1 and one of them gives B1. So at the best, we get the mixture of products. So practically, it's useless. That's my point. So we are not happy with this B1, C1, D1 pathway. Also, we eliminated B2, C2, D2 pathway. So what we can do here, we will take a look at the final structure, because we are quite close, right? We are around, we have some idea about B, C, D, and then there's only E, and then the final structure. So we can actually try going backwards, because last reaction is quite easy. It's Green's reaction, right? Yeah. We also get, we can go backwards, and as you can see, this is our final structure, and we can just go backwards. Basically, if you apply Green reagent, methyl magnesium bromide, and then work up, you will get this one. So it's really easy to get this structure. And we also get molecular formula for E. And comparing this molecular formula for E with that of D tells us that they differ by only a CH2 group. Okay, so there's like 14 carbon, there's 13 carbon, and 22 hydrogen, 20 hydrogen. So one CH2 group difference, okay, between this guy and this guy, there's one CH2 group difference. So indeed, the role of CH2N2 here is going to be homologation. Okay, homologation means you are getting another homologue from the previous one. Okay, and homologues are the compounds that differ from each other by CH2 group. So which means they have the same functional group, same backbone. You just extend the chain by one more carbon. Okay. So identify the role of CH2N2 as homologation. So specifically in this case, it's a ring enlargement, okay? Because as you can see, there's like 7-membered ring here, and nowhere here in this sequence we have a chance to have this kind of ring enlargement, because all the way, like let's say this is our pathway, okay? We get from X, A, B, C, D, and then E, and the final structure. In none of these pathways, we have a reagent, we have reaction conditions that can facilitate this ring enlargement. So this CH2N2 is the only step that can introduce one more carbon, and at the same time enlarge the ring from 6-membered to 7-membered. Okay, we mainly have, as I said, 6-membered rings throughout the whole pathway, but suddenly we have got 7-membered ring at the end. So the step DE is the one that could be responsible for this. So CH2N2 facilitates the ring expansion of cyclic ketones, and mechanism for which I will show at the end of the subproblem. So going backwards, we shrink the 7-membered ring in E to get D. Okay, something like this. Okay, so this is the real D. Okay. and then this is expanded, just one more CH2 group. D doesn't match to D1 candidate here. If we think that the D1 is the answer, we were already having suspicions about this not being a practically useless. Now it's impossible because we cannot go from D1 to E and then the final structure, right? So we eliminate this pathway too, okay? And we have to think other possibilities, okay? So it's all about this installation of methyl groups here, actually. So because B1 didn't work, B2 didn't work, but are these the only options we can have for methylation, for more specifically for negative charge formation? So let's think about this possibility. You have A, right? And when you go from A to B, you are having tetrobutoxide, right? And methyl iodide as nucleophile. So it's for sure that we are going to have some negative charge, and then that negative charge is going to attack methyl iodide twice. But what are all of the possibilities? Have you gone through them? So we have this compound A, and as we know, these hydrogens here are acidic because when base comes with its negative charge lone pair, it takes this goes here, this goes here, this goes here. And then we end up with a negative charge on oxygen. Okay, negative charge on oxygen. This double bond here, yes, like this. Okay, so this is our enolate. Okay, and the base leaves as base hydrogen plus form. Okay, and now we are writing this resonance structures for this again. We should have this double-headed arrow closed by brackets. So this goes here maybe, and this goes here. That's one resonance structure that we didn't talk about. So this could be the key for our scheme. And then another one is this going here, which we already talked about. Yeah. So we have the three possibilities, and we have talked about, I mean, here the negative charge is on oxygen. I mean, we can have all methyl. Technically, it's possible, but you know, it doesn't match with the final structure. So we are sure that it's a carbon attack. So we eliminate this from possibility of attacks, like there's no oxygen attack here. So we talked about this methylated here, but it just gives this B2, but it didn't make any sense because B2 and D2 were same. So we also eliminate this, but we never talked about this one. So we are posing our third candidate, B3, where methyl groups come here. Then we are getting rid of this oxygen with Wolff-Kishner reduction. So we end up with this, and then we are oxidizing this one, and then we get this compound. And then if you flip D3 again, you would see that it is same as D. It's exactly the same. So this is a real D, okay? And then we end up with this final structures for this, for all ciphered compounds. So B3, C3, and D3 are actually BCD, but I kept it that way to emphasize that the third option out of the proposed candidates is the real one. If you just compare B3 and D3, you know, and if you flip one of them, you will see that you can that the carbonyl and carbon-carbon double bond shift has occurred. Okay, and now I want to talk about this C to D, this oxidation. Actually, almost any combination of chromate salts and acids. For example, I can give examples of like potassium dichromate, H2SO4, or this combination, or chromium oxide in the presence of acid. So they all give chromic acid, H2 chromium O4. Okay, so we call it chromic acid, and we say that this chromic acid is made in situ, in the reaction flask. Okay, you are not preparing this and then adding it to, for example, C in this case. You are mixing everything together. Okay, and there's a reaction between these two that produces H2 chromium O4, and then with the loss of water, it becomes chromium O3. And this chromium O3 is the one that facilitates, for example, alcohol oxidation. That's widely used in these type of organic synthesis problems, like Jones oxidation. So for example, you have primary alcohol, any combination of this chromate, salts, and acid, you go all the way to, for example, in the case of primary alcohols, you go all the way to a carboxylic acid. In the secondary alcohol, you go ketone, and so on. But here it has different reactivity. There's like allylic carbon, and this is oxidized to ketone. So this is actually similar to the reactivity observed in the reaction between selenium oxide and alkenes when you have 4+2 cycloaddition. Okay, as you can see here in the second step. This is advanced reaction that we do not see in basic organic chemistry. That's also one way for us to learn more and more reactions when we solve these kind of Olympiad problems. Not only the basically higher difficulty levels of the reactions that we have covered so far, but also learn some new reactions, also identify similarities between reactivities that we have learned so far. So here, this selenium dioxide, it reacts with this, this allylic position, this carbon-hydrogen bond is reactive here in this case. So there's this 4+2 cycloaddition, and you end up with this. And then there's this shift, there is CO double bond attacking this carbon-carbon, then it shifts here, and then the carbon-selenium bonds breaks, and you get this one, and then probably through some kind of hydrolysis, maybe water attacks to selenium, and then the selenium-oxygen bond breaks, and you end up with alcohol. And then this, because there's like, you have the selenium dioxide, the oxidizing agent in the system, so this primary alcohol goes to the ketone. So probably in the case of selenium oxide, since you have this methyl here, this methyl, so this is, I want you to focus on this part. So you had methyl, and then you activated basically one of the CH bonds, and you converted it to alcohol. This is the first step of oxidation, and then basically methyl became a primary alcohol, and then it's oxidized up to aldehyde, not until carboxylic acid. But we know that when you have chromium-based reagents without any reactivity reducer, like pyridinium chlorochromate, there's like it's also chromium-based reagent, but its reactivity is reduced, so it goes only to aldehyde in the case of alcohols. But usually when you use this chromic acid-based, let's say, oxidation, it goes all the way to carboxylic acid. So in this case, it does not go, but probably in the case of chromic acid case, primary alcohols goes all the way to the acid. But that's not relevant here because this is just an example I took from the Advanced Organic Chemistry textbook to show the case of methyl going to primary alcohol and then goes to aldehyde and stops there with selenium oxide. But here, it's not relevant because we have secondary. It's not methyl, it's like CH2. So we are going to have OH, and then this OH will go to ketone, like this, okay? The mechanism is going to be really, really similar. So instead of selenium, you will have chromium, oxygen, 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 and the rest will be really, really similar. So just like here, selenium transfers one of its oxygen to this basically carbon, as you can see here in this step. It's going to be same with chromium. Chromium trioxide will transfer one of its oxygen to there and will oxidize it, okay? And the next thing I would like to talk about is going from D to E. So that's called ring expansion of cyclic ketones. The reaction mechanism is really simple. So I'm showing it with the cyclohexanone. Again, there's like a negative charge on CH2. There's also another resonance form for this, that this goes here and this goes here, and you have this where you are basically transforming the negative charge from carbon to the nitrogen at the other end. That's also another resonance structure, but usually we are having a negative charge on carbon in this kind of reactions. This attacks here, this goes up, and then this nitrogen leaves, okay? And then you see this evolution of nitrogen gas, and then there is this carbocation rearrangement, okay? Carbocation rearrangement in synchronous with this oxygen minus coming back, that double bond, carbon-oxygen double bond formation, and ring is expanded to cycloheptanone from hexanone, okay? So how do we think about it? So it's ideal that we know about this reaction in advance, okay? So which means by solving a lot of problems or maybe by reading advanced organic chemistry textbook. But in general, I'm showing this mechanism for you to learn. They don't ask about the mechanism. So it's difficult to actually think about this mechanism maybe for early organic chemistry learners. But just by looking at the mechanism, you should have an idea that yes, the CH2, maybe this is the one that's responsible for this ring enlargement. So I did not need to know the mechanism when I proposed. And actually, we found all structure for all compounds without knowing the exact mechanism for D2E. We just know that CH2 is there being added to a 6-membered ring to make it a 7-membered ring. So I'm giving this for you so that you can learn. And the next time you can say that, oh, there's one more role of CH2 and 2 maybe could be applicable in that problem that you are solving. But in general, you should be able to guess the outcomes of the reactions that you have never seen before, and you should be able to propose rough mechanisms. It's not 100% correct, but you should be able to come up with some chemically reasonable mechanisms to support what's going on. And here it makes perfect sense because we have seen that in almost all reactions that this CH2N2 reagent participates, this N2 leaves. Leaving N2 maybe leaves this positively charged carbon, which is extremely unstable. So that's why carbocation rearrangement seems plausible here. And also 7-membered ring is not less stable than 6-membered ring. In terms of overall stability comparison we make from 3-membered ring all the way to, let's say, 10-membered rings. I mean, obviously 5 and 6 are the most stable one, but still 5, 6, 7, these are commonly encountered ring structures in the compounds. As you can see, for example, in this specific compound, you have this 7-membered ring and it's perfectly stable. And now we are done with subproblem number 2. And then we can start subproblem number 3. As you can see here, we have these 2 pieces of information. So we are going to solve this systematically, right? So we see that there's a schema, and in the in the preceding part of the scheme, we only have two pieces of information: the fact that F is dibromoalkene, and then there is some information about NMR spectrum and also ozonolysis product that can give us some insight about towards the structure of F. So we have a synthesis, and there they ask us to decipher these compounds, and there's no any information here. So we have scheme, we have additional information about F next to the scheme, that it's dibromoalkene. It has two signals with 2:3 ratio, and it has acetone. It's good to draw acetone here as one of the ozonolysis product. And then what we do next is labeling the reagents with their typical role. Okay, so the most obvious one would be formation of J here. Okay, because problem specifically mentions that Robinson annulation is used in the synthesis of isonoocatone. So our final structure. And the next one would be this carbonyl protection via acetal formation. We have this. This is ethylene glycol, right? So ethylene glycol with two OH and in acidic environment. So it's most certainly it's used for protection of carbonyl. And then we have lithium aluminum hydride that's being used in the reduction. Okay. So these are the most obvious one, and also we calculate HDI for compound J, okay, because we are given molecular formula. It would be a good idea to have an understanding of the molecular structure in terms of HDI, and here it's 6, and what we can do is we can compare this 6 with the final structure, okay, and here it's 5, right? 1, 2, 2 rings, and 1, 2, 3, 3 double bonds, so a total of 5 HDI here, and here is 6, and judging from the number of oxygens, here there's only 1 oxygen, and here there are 3 oxygens, so we might suggest that this has maybe one extra carbonyl bond. You know, that's possibility. Judging from the number of oxygens, it might have one more ring. We don't know, but you know, potentially it has one more carbonyl group. And usually, when you have HDI 6, which is higher than 4, we usually say, oh, it has aromatic ring, right? Yeah, here we can see that it's a Robinson annulation. We probably get already our 2 annulated rings in J, so we don't have any. So this all 6 are coming from the double bonds and 2 rings. Okay. Anyway, so this is the information we can get from the molecular formula of J. And as you can see, solving this scheme is quite challenging, since we not only have any intermediate structures that could help us, but we also lack the structure of the starting compound F. That means we have to combine the given pieces of information here so that we can propose a structure for F. That's the only possible starting point for this scheme. We cannot like go backwards all the way to F. We can judge from for example, given molecular formula for J, we can judge some like a carbon content maybe of F, or choose from different possibilities of F using this information. But in general, we should be able to find the structure of F before starting solving this scheme. So we can start from the fact that acetone as one of the ozonolysis product, right? So we can propose a generic structure like this. Here, I would like to show that we can have anything here. So that's why I use this wavy bonds, okay? This is how you can show the generic structure, right? That you expect 2 methyl groups here and a carbon-carbon double bond, but you don't know what you have in this vinylic position. So that's why you use this wavy bonds. And we have 2:3 ratio, okay? So which means we only have 2 different kinds of proton, 2 different kinds of hydrogen in this compound, okay? So we already have like 3 hydrogens here and 3 hydrogens here, the total of 6 hydrogens here. And in order to have only 2 types of protons, we should have a symmetric compound, okay? So that means the right-hand side and left-hand side, or maybe top and bottom, should be same with each other. So the only possible structure, that's dibromoalkene. I mean, we already satisfied this alkene requirement by saying a double bond, which also matches with ozonolysis, because, you know, you apply this ozonolysis to either alkene or alkynes, mostly alkenes, okay? So we already satisfied this requirement, and we don't have any bromine yet, okay? And in order to satisfy these all requirements, there's only one possible structure. It's this one, okay? 6 hydrogens are here and 4 hydrogens are here. So that's like 2:3 ratio, okay? This is the only possibility. Alternatively, we can use a generic formula for dibromoalkene, okay? So we know that it's alkene, right? So alkenes usually have, for n carbon atoms, you have 2n hydrogens. But since we also have 2 bromine, we are saying that it has 2n minus 2 hydrogens. So this is a generic formula for dibromoalkene, okay? And since we have 2 signals, 2:3 ratio, that means it's a multiple of 5. We don't know it's either 2:3 or 6:4 or 6:9, right? That's also a 2:3 ratio. So it could be any of these. So we are just writing that we have 5 M hydrogens. So M here is arbitrary number starting from 1. It could be 1, 2, 3, and so forth, so on, right? 5, 10, 15, okay? This is gonna be the number of hydrogens we can have. And then what we are doing is we are making it equal, okay? 2n minus 2 is equal to 5m. And this n and m are just integers, right? Starting from 1. And simplifying this gives us n is equal to 2.5 m plus 1. And we start putting values of m. I said m and n are integer that can start from 1. But here, if you just put odd numbers to m, which is going to be like, let's say if you put 1, small as possible, it's going to be 2.5 plus 1, which is 3.5, and it's impossible, right? N shows the number of carbon atoms, and it should be integer. So m should be even numbers, right? 2, 4, 6. And when you put 2, n becomes 6. When you put 4 to m, n becomes 11, and so on. And we are choosing this first one, and we propose a formula for C6H10 bromine 2, okay? And we are choosing as X. We could have chosen the second one, but as you can see, the molecular formula for J is 16. Imagine the compound F has 11 carbon atoms. I mean, it's impossible, this one. This one is already impossible, like 16 carbon atoms, because as you can see, we are going to add, let's say, at least 1 or 2 carbon atoms here, and then there is this methanol. We are not exactly sure what's going to do, but we are expecting to have to combine F with this reagent and then add carbons later on. So having 11 and 16, they do not work, okay? What you can do is you can find the number of carbon atoms in I, because we know that this is Robinson annihilation, and Robinson annihilation adds the number of carbon atoms of all the reagents. So here we have 1, 2, 3, 4, 5, and here is 16. So which means I should have 11 carbon atoms. And if F is already having 11 carbon atoms here, okay, then that means from F to G, from G to H, we don't add any carbon atom, which seems difficult here, okay? So that's why we are choosing this molecular formula. And when you work out this molecular formula, you can actually draw all isomers for this molecular formula, all isomers that could give acetone as ozonolysis product. So basically, you can draw all isomers for this molecular formula having this moiety, which means you already can account for 1, 2, 3, 4 carbon atoms. That's relatively easier for you to draw the rest of it, okay? So this is just the second way for you to find out the structure. And again, this looks similar to inorganic chemistry, where we are setting up equations where number of unknowns are higher than the number of equations that we have. So, but here we are sure that, for example, n here should be integer, and m is also integer here. So using that, we can actually arrive at the molecular formula. So now that we have the structure for starting compound F, which is here, we can try to decipher the scheme. But before that, it would be a good idea to align the structures of intermediates or reagents with that of the final structure. For example, we can clearly see that this dimethyl moiety that you see here actually is represented in the final structure. So that's what you can see. This is how am I going to show you. As you can see, this part 1, 2, 3, 4, 5, 6 carbon atoms are actually here, okay? And you can also see that this guy, you see, it's also here. And that leaves us 4 carbon atoms that are unaccounted. So in the final structure, we can actually see that 1, 2, 3, 4, 5 carbon atoms are coming from this reagent, and 1, 2, 3, 4, 5, 6 carbon atoms are coming from F. So there's like 4 carbon atoms that are probably coming somewhere in the scheme. This means that this series of synthesis brings a net 4 additional carbons. That does not mean that we are only going to add 4. I'm saying net 4, which means you can have maybe add 5 carbon atoms and 1 carbon atom somewhere, maybe during the hydrolysis or some others that we don't know. But the net 4 additional carbon atoms are being incorporated into these structures to make this final structure, okay? This, what I call as alignment analysis, is necessary when solving organic chemistry synthesis problems to keep track even before starting the synthesis, okay? So we haven't started anything, we only find out the structure of F, but now we are doing this alignment just to keep track of what is going on, keep track of main backbone. Furthermore, to make an efficient use of molecular formula for J, we can actually deduce the molecular formula for preceding compound I, because we know that this step is Robinson annihilation, okay? So what we do is we subtract the molecular formula of conjugated ketone, which is like C5H8O. We subtract this molecular formula of conjugated ketone from the molecular formula of J, which is 16 carbon, 3 oxygen, and 22 hydrogen. And then we add the molecular formula of H2O. Why? Because during the process, 1 molecule of water is lost for every molecule of the annulated ring that's being formed. For every molecule of J that we are forming, we are losing 1 molecule of water. Okay? So by applying this, we can actually have the molecular formula for compound I. And we can see that it has 11 carbon atoms. Okay? The reason why we know that this whole conjugated ketone actually lies in here is because we know about Robinson annihilation. We know that Robinson annihilation happens probably in compound I. It's something like this. and it has a negative charge here, I'm seeing something like this when I say the backbone is like this. Maybe there's some additional moieties, additional function groups, but it has a backbone like this, and it has an alpha proton here, and we make a negative charge here, and we attack from here. And it's going to attack from here, this goes here, this goes here. So we already know that, right? And the double bonds basically disappears. I mean, it just goes here, it goes here, right? That's how we know that. That's how we know Robinson annihilation works. So there's probably a negative charge, and this attacks from here, this comes here, this comes here. That's what I'm saying. And that's how this whole moiety lives in this compound. The reason why we are doing this is because we know what happens in Robinson annihilation. So up until now, we established the structure of F and molecular formula for I. And through an alignment analysis, we also identified the source of 11 out of 15 carbon atoms in the final structures. Okay, we only don't know where these 4 are coming from and how they are incorporated, but we were able to identify the source of 11 carbon atoms. And the reason why you could have said that, oh, we already know J, why we know I, but it's the thing is that I will show you that this part is really difficult, FGH, and the more we can go towards the left part of the synthesis, much better. Okay, so at this point we are sure that this is Robinson annihilation. So by working out the formula for I, we are making it easier to establish the structure of F, G, and H by knowing the molecular formula of I rather than further compound that's J. So that's why. If it was possible for us to move even further to the starting point, we could have worked out the molecular formula of H or even G, let's say it's possible, so that we can actually make this problem solving much easier. Okay, so that's why we did this to find the molecular formula for I. So the most difficult part of the scheme is the first 3 steps. And I will explain why. So let's start applying first principles and try to get GHI, just continue down the line, Robinson annihilation and this. Obviously, the first step is simple SN2, right? So we have bromine here, and then this is just, I'm going to write in open form, COO ethyl, COO ethyl, and then there's negative charge, and this is like basically a salt with sodium plus, and this negative charge attacks the carbon and bromine leaves, okay? And then we end up with a new carbon-carbon bond that's being formed, and then we have ester hydrolysis because we have hydrogen plus, which shows the ester hydrolysis under acidic condition because we have 2 ester groups, and followed by decarboxylation to give us G. And I just wrote as G1 again because of probably many possibilities. I'm numbering it as G1 and G2 and so on. So we have G1, and this G1 is basically nucleophilic attack of this salt to one of the carbons because it's symmetric, it doesn't really matter, and bromine leaves. And then we have ester hydrolysis followed by decarboxylation. Usually, decarboxylation requires high temperatures indicated by maybe T signal or maybe delta like this, just to show that it's being conducted at high temperatures and carbon dioxide is being low. So that's how it happens. So we first get bromine, and then this double bond here, and here, COO. After hydrolysis, we get this, and then this goes here, and then this goes basically to take this hydrogen, okay? So you end up leaving minus carbon dioxide, and then you get this product, okay? So you are basically breaking this carbon-carbon bond. You can actually use both cases at the same time, the decarboxylation and without the decarboxylation, because we are skeptical, right? We are not sure because they haven't shown this temperature. If they have put this T signal there to indicate higher temperatures, that's definitely this. But since there's no temperature, I am a bit skeptical, so we can also have this case as well, okay? And the next step is, because whatever the case, the G is carboxylic acid. Maybe monocarboxylic acid or decarboxylic acid, we are not sure, but it should be the carboxylic acid. And then reacting with methanol under hydrogen plus, we are getting ester. We are making ester, but this time it was actually ester before. It was ethyl ester, but now we are making methyl ester. So the difference between this one and the H is that they are both ester, but one of them is ethyl and one of them is methyl ester. Okay, so and I'm gonna continue with only this, but we can have this parallel. We can just go, but I'm 100% sure that this is not gonna work. So I will just continue from G1 that I showed you here, and then we get this one. So this is our G1, and then this OH becomes O-methyl. This is just a Fischer esterification. Okay, that the carboxylic acid becomes an ester, and then, using this sodium hydride, we only have one possibility, and that's where there is a negative charge here, because there's only one acidic proton, right? That's alpha proton. This attacks to carbon and bromine leaves, and you have this, which is 4-membered ring. It's very unstable, okay? And then in the final structure, you do not have 4-membered ring. So that's why, we will eliminate this possibility. The reason why I only show that this is the only possibility is because we don't have bromine in our structure, right? So it's impossible. And there are many reasons why it doesn't work, right? There's like, we should have 3 oxygens, but we have only 2. We should have 11 carbon atoms, but we only have 9. So that doesn't work. But what we learned from this speculation, let's say, is that from F to G, we are adding plus 2 carbon atoms with the decarboxylation case, okay? When we have decarboxylation, we are adding plus 2 carbon atoms, right? As you can see, we have 1, 2, 3, 4, 5, 6 carbon atoms in F, but here we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so from F to G, we are adding 2 carbon atoms. So the point of this reagent is to bring 2 carbon atoms, if you use 1 equivalent of each of them. And then from G to H, we're adding 1 carbon atom, okay, as a methyl group from carboxylic acid to methyl ester. So from F to H, we have 3 carbon atoms. So initially we have 6, now we have 9, but these 9 carbon atoms are less than 11 that we need to have for I. So that's why we are eliminating this pathway. But it it's really good idea to be able to get this kind of table, like by working out, because that's gonna be the first step that you will try. Okay, it doesn't really matter if it works or not. That's how we are thinking, right? That's also how I also solved the problem, right? By applying this, what's gonna happen, even before starting worrying about this final structure alignment, just to see what's gonna happen if I try to apply all the way to I, and I see that it doesn't align, it's 4-membered ring, nothing here, but I can just see that F to G gives me 2 carbon atoms, and G to H gives me plus 1. So now, what I can do is, so as you can see, it's quite difficult to decipher the first part, okay, and propose the structures to match with the given formula. But the part after J is relatively easy. The reason why I'm not continuing for this part is because we will start trying to align the structures that we propose with the final structure, and we have a lot to do after I. Okay, we have to do Robinson annulation, then J, K, L, M. So we cannot guarantee that, you know, additional carbon atoms are not being incorporated, or I don't know where this oxygen is coming from. Is there a new ring formation, and so on. So I just want to show you that if you get to J, I mean I actually, then Robinson annulation J, that this part is relatively easy. Let's analyze. Okay, so here you have carbonyl protection. So that means probably there's like some carbonyl group, you are protecting it and then reducing. Okay, so lithium aluminum hydride is a strong reducing agent. So it reduces like aldehydes, ketones, esters, amides, everything basically. And in the case of, in all cases except amides, you get alcohol, right? In the case of amide, you get like amide becomes amine, right? We are not talking about amides here because, as you can see, there is no nitrogen here. We are 100% sure that it's not going to be amide reduction. Okay, so it's probably one of those ester or maybe alcohol, aldehyde, ketone. So whatever happens here is that you are having some carbonyl group, and that's being reduced to alcohol. So you end up with alcohol here, and this one is methyl chloride, right? So the point of lithium aluminum hydride here is to make alcohol, and then with methyl chloride you end up with O-methyl. So this L certainly will be O-methyl, and then you have lithium NH3, then ethanol to M, and then this hydrogen plus. So hydrogen plus is probably to protect another CO group that's not being reduced. In this case, this guy. Okay, so this guy is probably also here. I mean, that's certainly there because this comes from this one. So that's in J, okay? And this is the carbonyl group that we are protecting here at this step because we do not want to reduce and do something else. So that means in J, we have something CO group maybe, okay? And so let's say here, and that CO group, I'm talking about the structure of J. I'm trying to propose a partial structure for J, something like this. And that CO group is becoming O-methyl from K to L. And then what could this do? Lithium and in liquid ammonia probably, and then there's ethanol. So that's the source of electron. We have seen this like sodium in liquid ammonia to use this, for example, from the triple bond to double bond. We have seen this reaction, right? In the liquid ammonia, sodium metal in liquid ammonia, where this that's basically a source of electrons. Okay, so here it's the similar thing. So here we, instead of sodium, we have lithium, right? And this lithium is gonna produce a lithium plus and will give some electrons. And those electrons are gonna reduce this O-methyl. Because also, as you can see here, the number of oxygens are being reduced. There are 3 oxygens, okay? And then in the final structure, there's only 1 oxygen. I mean, this oxygen, right? So we are getting rid of oxygen, actually, and also 1 carbon atom through this process, okay? So if this is like CO in J, if you have CO, and then this becomes O-methyl, after reduction and methylation in compound L. And then this lithium NH3 methanol system, it's going to produce electron, and probably we will have something like this. Two electrons are attacking here, and O-methyl leaves. That's also reduction, actually, okay? So we have like a negative charge here, and then probably ethanol is producing its hydrogen plus, so that it's basically going from carbon, oxygen, methyl to carbon, hydrogen through lithium ammonia ethanol system. And then since you want this operation in one oxygen, you have protected the other one, and then you deprotect this one, and you get your final structure. So my point here is to show that from J to all the way to the final structure, it's just the operation on the same carbon, same oxygen, okay? It does not basically try to incorporate something additional, or through J to M, there is no any additional ring formation, double bond formation. It's just basically an operation on the carbon and oxygen, or maybe some carbonyl, to make it, to break that carbonyl bond, basically. First, from CO double bond, so we probably have this CO double bond here, to make it CO single bond, I mean here, CO methyl, and then CH. So that's the operation on a single, let's say, reaction center. So the reason why I'm telling you this is that you can just, when we think more about this step, we don't have to worry about what's going on here. Okay, this part is really, really easy. So every single step that I'm showing you here is actually giving very useful information. So this analysis gives us information that we can actually establish the backbone of final structure in compound J as like this. Okay, so I mean, it's exactly the same, honestly, but here I want to show this as a backbone. Okay, so maybe somewhere here there's, I don't know, something here, I don't know, maybe something here. I'm not 100% sure, right? So, or maybe here, but the backbone is like this. Okay, maybe one extra carbon somewhere here. Okay, because this is 16 and this is 15, right? There should be one extra carbon. And this should also give you an idea that why, because during this process, we are not eliminating any carbon, right? I mean, here we have CO, then it becomes COH, then CO methyl, and then the CH. So as you can see, this carbon is just there. Carbon, carbon, carbon. We are just getting rid of an oxygen. So in order to, in the reactions where we are losing a carbon atom, but then there is no any, decarboxylation or I don't know, any other thing, but just the reduction, that means it's an ester reduction. So it was like this, and lithium aluminum hydride reduce it to CH2OH. So we are losing this one carbon atom. So when you are having one less carbon atom and you have reduction with lithium aluminum hydride, that's most probably an ester reduction. Because if you remember, I told you that there is some carbonyl group. It could have been an aldehyde, it could have been a ketone, it could have been ester. So actually it's ester. Because in other ones, you are not losing any carbon atoms throughout the entire synthesis, right? If you can keep track of it, this one doesn't lose carbon. It actually brings carbon. I mean, we're going to deprotonate it anyway, but that doesn't give any carbon atom. That doesn't lose any carbon atom. Here, this is methylation. This is like carbon O methyl becoming carbon H. Again, you are not losing any carbon atoms. I mean, you are losing carbon atoms from methyl, but you actually incorporate it here, so that's fine. I'm talking about the backbone. So this is the only step that you can lose carbon atom, and that means that this K should be an ester. From step K to L, what you are making is you are methylating. You are making this OH into better living group to O methyl, and here lithium. Let's say 2 lithium goes to 2 lithium plus and giving 2 electrons, and those 2 electrons are attacking carbon, and then O methyl leaves. You can also propose a radical mechanism, but honestly, I prefer this kind of mechanism to, let's say, it also has some other bonds to remember this easier. And then you end up with negatively charged carbon, and then you have ethanol in the system, right? To provide hydrogen, and this minus takes this hydrogen, and then you end up with carbon hydrogen instead of carbon O methyl. So that's a reduction because you are reducing the number of carbon atoms to oxygen to more electronegative atom by 1. You had 1 bond, but now you have 0 bond. And also alternatively, you can say that you are increasing the number of bonds to the hydrogen, which is the definition of reduction in organic synthesis. And since we know that this is Robinson annihilation, we can actually propose a backbone for I as well. Okay, we can work backwards to propose a backbone for compound I. So this helps us to identify that we need actually 2 molecules of this reagent in order to make I. Okay, so this is again backbone. This has only 1 oxygen, so which means we have 2 more oxygens. That's probably COO methyl, right? Because here we have 6 and 7, 8, 9, 10. 10 carbon atoms, it should be 11. So maybe there's also COO methyl, I don't know, somewhere. So that we can have 2 oxygens and 1 carbon, which makes perfect sense, right? This should be methyl ester. So maybe it's like this, that maybe like this. like putting COO metal here completes the structure, right? It's like 1 and plus 6, it's 7, 8, 9, 10, and then 11 carbon, 1, 2, 3 oxygens, okay? And what's the HDI? 1, 2, 3, and 4. So 4 HDI, and here it's gonna be 11 multiplied by 2 plus 2 minus 16 divided by 2, which is 22, 24, it's also 4. So that's perfect. So this is gonna be probably the structure of I, but obviously we need to work that out, okay? But the reason why I just wanted to show you that this is really easy, this is just operation on a single reaction center. So that's why we can have a backbone for J and then backbone for I. And again, this I is coming from this guy, so we can also identify the sources of these 1, 2, 3, 4, 5, 6 carbon atoms as these, okay? And then we also know that F2G gives plus 2 carbon atoms, right? But we need 4 carbon atoms. So this helps us to identify that we need 2 equivalents of these reagents that's going to react with each bromine, okay, to extend this chain. I will show you that in the next slide. So I just put F and the final structure here. The first step is this one, and that's how it's gonna work, okay? So I'm gonna use 2 equivalents of this. This is gonna attack here, and bromine leaves, okay? And then I form something like this. Here I have bromine, okay? And then here I have this guy, COO ethyl, and then COO ethyl. And then with hydrogen plus, they both become COOH, and then with decarboxylation, I am getting rid of one of them, okay? So you end up with this, and then you are applying the same thing to the other one, because we are using 2 equivalents of this, and you end up with this structure of G that you see here. And then you have esterification, okay? So the COOHs are becoming COO methyl, and then here's the sodium hydride actually facilitates Dickmann condensation, Dickmann cyclization. It's actually Claisen condensation, but because it's intramolecular Claisen condensation, you call it Dickmann condensation. So it's actually CH2. It's actually CO2 methyl. I should have written it in the other way around, but that's just the COO methyl, and here it's COO methyl. And then here you make a negative charge, and this attacks here. This goes up, comes back, O methyl leaves, okay? And you end up with this I, and indeed this matches with the backbone that we have shown, okay? You already constructed this part, as you can see. And we already found out that these 4 carbon atoms, 1, 2, 3, 4, they're coming from these 2 equivalents of this guy, okay? 1, 2, 3, 4, okay? And then the rest is easy, right? You have Robinson annulation, and what's gonna happen is you have a negative charge here, because it's between 2 CO groups, and then this attacks here, this goes here, this goes here. This is a first Michael addition, and then you will have E1CB mechanism to lose water to form this compound, J. And then you see, you are protecting this carbonyl so that you can perform your operation. Because if you just directly add lithium aluminum hydride without protection, imagine we don't have this, you are adding lithium aluminum hydride directly to this guy. This is also going to be OH, then O-methyl, and then this could also be reduced, honestly. So you end up with CH here, just the alkane, basically. So that's why it's essential that you protect this group first, which is stable to all of these reagents, subsequent reagents. Then lithium aluminum hydride makes the COO methyl into CH2OH, and then this OH becomes O-methyl. So this is methyl group that we call it in organic chemistry, methyl, and you can also write it OMS, okay? And then you have this reaction where this electrons that you form from lithium attacks here, basically breaks carbon-oxygen bonds. You can also propose a radical mechanism for this one. It's like 2 electrons here. And then you end up with this M. So the last step is just that you need to deprotect this oxygen, this acetal, to make carbonyl bond, and that's going to be your final structure. So this is the final solution for this problem, and then we did subproblem 3 as well. That's everything for today's problem. If you have any question about any step, drop them in the comments and I will answer. This kind of thinking we used here is exactly what you need to develop for IChO 2026. If you want to take your preparation further with live sessions covering the IChO 2026 preparatory problems, the details are in the description. The first session is on June 6th. I hope to see you there. Take care.